We're going to talk about acids and bases as one of our final things to do for chemistry unit. We talked a little bit about them already, and we just talked about them a little bit as far as the nomenclature goes, and then some properties. So you did the lab on some of the properties associated with acids and bases, and then we'll also cover in this, I guess, connecting back to that lab about why we didn't do certain tests and so on. All right, so what exactly is an acid and a base? Acids and bases are important because they are used by humans and for industrial purposes. They're part of your body and so forth. So it's important to kind of know these certain types of substances. Acids are mainly used in industry to manufacture various products, so fertilizers, explosives, plastics, motor vehicles, circuitry for computers, and so on. So a lot of stuff. And bases, you typically find those in things like soaps, detergents, types of dyes, and so on. But to use these chemicals in some functional way that betters, hopefully, human society, you need to understand about what they are, and how they work, and what their properties are, and how they react, and so on. So we're going to do that today. Now, what we're going to cover is what we mentioned before. Um, Actually, maybe you didn't mention it before. We did talk a little bit about acids and bases, but we're going to cover I guess, an explanation for most acids and bases is Arrhenius versions. So Arrhenius was a scientist back in the day who did some research, I guess, into chemistry and including acids and bases. And he is now being here credited with describing what an acid is, and that's why these are called Arrhenius acids and bases, because they all follow a similar type of description about how they behave and what they're composed of and so on. Now, that's not to say that all acids and bases are Arrhenius acids and bases. Now, we're not going to touch on the other types of or other scientists that have found other things that don't fit Arrhenius's description. For instance, in grade 11 chemistry, you'll talk about Bronsted-Lowry, which is similar to Arrhenius's acids and bases, but it does include more things as being acids and bases, primarily for the bases. The acids are generally very clear cut for the most part, and bases are a little bit wonky in that they don't all have the same kind of chemical composition that you might find in acids. And then beyond Bronsted-Lowry, there can be other additions to incorporate other things that tend to act like acids and bases that wouldn't be included under Arrhenius's description and under Bronsted-Lowry's description. But anyway, Arrhenius has the most simplistic description of what comprises an acid and a base. So we're going to look at that, and then we'll build upon that in the future. But just keep in mind that this is not the be-all, end-all of all acids and bases. And maybe we'll touch on something like that a little bit later, just to mention about why. All right, so when hydrogen chloride, so here's hydrogen chloride here, dissolves in water, it does something which we call dissociating. And we mentioned this with part of our naming system. So when we were naming acids, so hydrochloric acid, it's not technically hydrochloric acid until it's put into water. Okay, so it becomes aqueous. You would have to take this gas and bubble it in, and it would dissolve into the water, and then it would act like the acid. Now, when the precursor to the acid, so the reactant that is, well, it's not even a reactant, it just dissolves. When it dissolves, what it means is it's breaking apart, so it's dissociating. So even though this is not ionic, when it's in water, it does act like it's ionic. So what that means is that this molecule um, breaks off into ions. Okay, you have hydrogen ion and chlorine ion. Okay? So this is called dissociating. When an ionic substance separates into its ions in water. This is true for sodium chloride as well. All right, if you threw sodium chloride into water, it would do this. And this is also dissociating. Okay, so there's no difference between these things, but now we're using this word to talk about acids and how they do this. And this is true of bases as well. So if you had BaOH. I'm not going to balance these. If I put that into water, it would form Ba2 plus OH minus, and so on. Okay, so this is all dissociating when some material separates into the ions that make that material up. Okay, the only reason we're talking about it here is because we're going to talk about what these ions do a little bit later. Okay, but that's what essentially happens in acids. You have a molecule that separates into ionic forms of its elements when it's placed into water. That's called dissociating. So you can see here's other uh, acids that do this. So over here, this would be, I guess, hydrochloric acid, right? Hydrochloric. Then you have hydrobromic. You have sulfuric acid. You have chloric acid. You can see it that they're all dissociated. Okay, so they break off into the positive ion, negative ion, positive ion, negative ion, positive ion, negative ion. Okay? So there's a pattern here, according to Arrhenius, about all the things that they notice as far as acids and their dissociations. Okay? So what Arrhenius ultimately decided in his category of acids and bases was that any substance that dissociates in water to produce one or more H plus ions. Okay? So his theory was any substance that we put in water that makes H plus ions, it's an acid. And if you look at the pattern here, you'll notice that all of these things, when you put them into water, they all make H plus ions. And that's the key thing, that they produce these H plus ions. Now, how did he discover that? You'd have to look at his research and so on. How would he know that these broke off into these specific things? You'd have to look at his research and so on. Okay? But that's what he found, and that's what he ultimately decided. Or that it was true, I suppose. Or it is true that anything that does dissociate, that does add these H pluses, is going to act like an acid. So any Arrhenius acid will increase the concentration of H plus ions in a solution. And remember, aqueous is just water. So for this reason, an Arrhenius acid must contain hydrogen as the source of H plus ions. And an Arrhenius base is a substance that when added to water, it will increase something different. It increases OH minuses in the water. So what that means is, in order to increase OH minuses or hydroxide ions, you typically have to have something that has an OH ion in it. And this is how we kind of described our bases before when we were doing our nomenclature, was that we looked at something like NaOH, sodium hydroxide, and if we put that into water and allowed it to dissociate, it would separate off into its positive and negative ion, and one of those ions here is an OH minus. So this would be an Arrhenius base because the OH minus is produced. Okay. All right. So the bases are the other pattern, right? So it's not increasing H plus ions. An Arrhenius base is one that, when it dissociates, increases the hydroxide ions. So to be an Arrhenius base, you must have an OH minus ions when they dissociate or in their formulas. So for this reason, that you have to have those as a source of OH minuses and so on. Okay. So when we go back to our understanding of acids and bases, typically anything with an H, when you throw it in water, will be an acid. And I think when we looked at most of our things that we looked at on the course, anything with an H was an acid. However, anything that has an OH minus or hydroxide ion, when you throw that into water to dissociate, it's going to produce OH minuses, which makes it Arrhenius base. Okay. We're also going to talk briefly about strong and weak acids here as well. The strength of an acid or base depends on the extent in which it ionizes. 8. So for instance, HCl, which will ionize completely, 100%, is into its ions over here. So that means that all of this is converted into all of these. So none of this remains. It's all going to be as its ions, and that's it. Whereas if you have a weak acid, it's only going to ionize partially, so that when this puts into solution here, you're only going to get some of these particular materials. You're also still going to have a bunch of HC2, H3OH2 hanging around in the solution as well. Okay. All right. So it'd be something like this, where these things are about like 1% of what dissociates, and then 99% of the original thing is still like this. If you go back to the strong acids, if you had this being thrown in, all of that material, there's none of it left. So there's none of the original hydrochloric acid left. It's all been converted into this. Okay. So this does no longer remains. It's purely in its ionic forms for the strong acids. And then for the weak acids, the acid only dissociates a small amount, about 1%, and the rest of the molecule that didn't dissociate are spread out in the solution. So that's the differentiation between a strong and a weak acid. So strength is the extent to which it ionizes, which really means dissociates. Strong acids do it 100%, so this would be a strong acid. And a weak acid only partially ionizes or dissociates. And this is evident in the diagram there. Okay, so if you ever hear the term strong and weak acids, that's what it's referring to. Now we're going to talk about the significance of those in a little bit. But for now, there's the diagram to represent that. So this is your pre-dissociated acid. And I know it's an acid because it has an H. And when it dissociates, it's going to form H plus ions. Okay. Now, I know the colors aren't going to work out great for us here because this is all black and white, but we'll do our best. This is a reasonable diagram down here, although this is a little clearer over here. But what this is showing here for A is that if this is your acid, when it dissociates, you can see that there's no more HA. There's only H pluses and A minuses, which are the negative ion of the acid, and that's the H plus. Okay. If you look at the weak acids, you can see that here's your acid here, and most of that acid remains. There's only a small proportion of the ionized particles. Okay. So the strength is based on that. Okay. So for the strong acid, okay, and then over here you have the weak acid. Okay. So there's a couple reasons why this matters, that it doesn't dissociate as much. For one thing, it's going to be affecting the pH, which we're going to mention just here. We're also going to talk about corrosiveness as it applies to corroding something, including being dangerous and so on to humans. All right, now, you've probably already heard of pH, and maybe you dealt with it last year in grade 9. There's a pH scale that measures how acidic something is in solution. Okay. Now, the scale ranges from 0 to 14. It's a logarithmic scale where each number is an increase of 10. So if you went from 7 to 8, this is a times 10, more concentrated in whatever we're looking at. Okay, we'll talk about that in a little bit. Okay. pH is a measure of H plus in the solution. So if I increase a concentration like this, it might have to do with the amount of H plus. Now, this is going lower in that scale, so this would mean that there's a 10-fold decrease in H plus. We'll talk about that later. Okay. Now, because strong acids dissociate completely, they usually produce pHs of 1 and 2, because if you're dissociating into all those ions, you're going to make a whole whack more of those ions. So you're going to be at the high end of the acidity or pH scale. Whereas weak acids, they don't make so many of those ions, those H plus ions, so they're going to be lower on that scale, like a 5 or a 6, because they're just not producing as many of those ions. But we'll look at the pH scale in more detail in just a moment. All right. Now we're also going to tie strong acids into the idea of corrosiveness as well, and also weak acids. You've probably heard that acids are corrosive, and so are bases, and other materials can be as well, but primarily this is going to be associated with acids and bases. But what does it mean when something is corrosive? Well, in simplistic terms, all that it really means is that the corrosive material is going to react with something else. This is nothing out of the ordinary. That's what chemicals do, is they react together. However, these corrosive things can also react with living tissue, and that's what we're going to talk about today. So we're going to be talking about how they react with living tissue. Because we're alive, so corrosive things could potentially pose a threat to us, so we have to be aware of them. Now, the symbol over here is the WHMIS symbol. So this is kind of the workplace hazardous materials information symbols. And this is for a corrosive. Note that this symbol applies to materials that you might find around your workplace, home, or whatnot, and it also applies to the human body. Okay? So, human body here, human body here. So that's why we want to pay particular attention to anything that's corrosive, because if they come in contact with your body, they could perform a chemical reaction. Now, this symbol typically over here is usually metals. So typically corroded things are also going to react with metals. So metals and living tissue, two of the best things you can find. So if you see anything that has the symbol on it, a product you have at home, a cleaning product, a industrial products, just anything, be wary of that warning. Okay? All right. Now, I've always wanted this addressed, so we're going to address it here so that you know. What does it mean when living tissue gets corroded, or why should you be concerned about corrosion, and how does it affect living tissue? So acidic solutions or acid solutions contain H plus ions, which we talked about, right? The acids dissociate, right? So this is our dissociate. But the H plus ion doesn't stay by itself. So what actually happens is water takes that H plus ion and forms this thing over here, which is called hydronium ion. So the H pluses don't exist just by themselves. They will be picked up by water, at least to some degree, or how many are in there. They're going to be picked up by the water, and they're going to become this hydronium ion. Okay. When these hydronium ions come in contact with your body, they will react with your proteins and lipids. And that's not a good thing, because you want your proteins and lipids to be stable and stay in the form that they are in, because they give you structure and composition. And if you disrupt those molecules through a chemical reaction, you're now removing your proteins and lipids into some other products that are formed, and they're not going to be conducive to maintaining structures and so on. So the proteins and lipids, if exposed to hydronium ion, to acids, will be broken down by this action, and that's not a good thing. So H3O, so hydronium ion plus protein, is going to result in maybe potentially a chemical burn. It could also be irritation. Now, corrosive materials that affect living tissue, we call them caustic. So caustic. So if something's corrosive, you might also hear it being referred to as caustic, because it's going to have some biological effect on your body. At low concentrations, caustic materials are usually called a skin irritant. So these are not severe kind of situations, but they could be swelling and redness. blotches. There could be some pain, maybe burning and so on, sensation, but it's nothing too major. However, at high concentrations, caustic materials can cause chemical burns. Okay? And these are going to erode your tissue. And I assume, well, it's non-severe chemical burns, I guess, because there's going to be degrees of them. Um, are Can be reversible, but some of them, the damage can be extensive depending on the degree. So, could be irreversible burns and so on. Okay. Now, any material that has this symbol up here, so the one that I just showed you, can corrode rapidly metals and skin. So what that means is they have that warning there, not just because it's corrosive and can cause irritation, but because it can leave a chemical burn and it can happen immediately upon contact. And that's why we have those symbols to let us know about that you want to take certain precautions when it comes to dealing with those. Now, you will notice here that this is a strong acid. Um, that we'll mention that it's a strong acid. So you have less to worry about with weak acids. Weak acids probably cause more of an irritation and so on. Um, they're not going to be corroding quite as much when it comes to uh, chemical your body. So this is mostly to be concerned about with the strong acids and bases. In this case, a strong acid. Now, acids can also turn gaseous. So some corrosive materials, acids, are volatile and can emit a corrosive mist upon contact with the air. So that comes up out of solution or out off material. So here's your thing here, and then you can get this corrosive mist coming off of it. And you can smell that mist and so on. But anyway, the smell is coming from that mist, and you have to be wary of the mist because these mists, if you inhale them into your respiratory tract, they will then do their damage to your respiratory tract, irritating, potentially burn, and so on. Okay. So this is why you should always waft a gas in order to smell it. When you get a lower, so that you get a lower concentration of a potentially hazardous gas and not a high concentration. So wafting is when you kind of move your hand through a gas container, so your hand travels by the gas, and then it knocks the gas closer to your nose. But then the process is diffusing it around, lowering the concentration. And you don't want your nose right here because you're going to get a high dose of that gas. So you want to waft it away and then smell it later or in an adjacent vicinity of where you are. But you don't want to put your nose directly over the gas because you're going to get a really concentrated amount of that corrosive mist. All right, the last thing we're going to mention here about safety is eyes. Now, corrosive materials can react with your skin, they can react with your respiratory system, and it can also react with your eyes. They can cause ultimately blindness, as these react with the cornea. Now, the cornea is the part of your eye, and we'll look at the eye later when we get to optics after we've seen it, but the cornea is really kind of like your opening, the covering on your eye, right? And under it is the lens. So here's the lens. Here is your pupil, right, or your where the light travels through. This is your lens, right, and then this is your retina at the back, and so on. So you're going to be dealing with this situation up here. So that layer, that transparent layer, that's on the outside layer of your eye, is the cornea. And what these corrosive materials do is they can cause scarring in your cornea, and it reduces the transparency. So essentially, the cornea can be rendered opaque. Because of the scarring, which means that no light can transmit through it. And you would be effectively blind in that eye unless you can get a new cornea, which I don't know if that exists or not. So that is something to be aware of. So we just briefly looked at what an acid is, what a base is under Arrhenius' theory, which goes a lot with the nomenclature we did. We looked at the idea of strong and weak acids and bases and how they dissociate, so 100% versus a smaller quantity of dissociation, and that gives the ultimate strength. We briefly mentioned pH, which is the measure of those amounts, and then we talked about safety as far as it applies to corroding living tissue and why you have to make sure that you're doing everything you can to not be exposed to any of these corrosive materials.